So welcome, I'm Mike Morrow. I'm president of the St. John's Center of the RESC, which most of you probably figured out. And I'm going to start with an acknowledgement. Beautiful land together. When we meet in person, we usually go around and do a quick round of introductions. So why don't we do that? So I've already said I'm Mike Morrow, and I'll encourage people who are online to mute until we sort of ask you to unmute. And we'll be introducing this guy soon anyways, but you can introduce yourself. And I think I got most of the people there. And I think most of the people that I saw are members, but I'll just say a little bit about membership in a minute. So just a couple announcements before we go on to Terry's talk. The meeting in December is, and if people online, if there's any problem with hearing me or anything, just be sure to let me know. So the meeting in December is going to be the second Wednesday instead of the third Wednesday. That moves us a little bit away from Christmas. And the speaker is apparently going to be me. And I'm going to talk about the Lucy mission to the Trojan asteroids, which has launched and has launched a year ago, but isn't going to start doing anything. Well, it's doing lots, but it's not going to get to the asteroids for a few more years. But I'm going to say a bit about that, and there might be some socializing and some treats as well. And I'd also like to remind people that there are opportunities to get involved with the center. There are sort of three main committees: the Light Pollution Abatement Committee, the Dark Sky Preserves, the Observatory Committee. And I encourage people, if you want to get involved in the center, find out how things work. You don't actually need to know anything. You can get involved, just sort of see what is going on. I don't think any of them are very onerous. And the other volunteer opportunity is to stand at the front sometime and give a talk. And again, you don't need to know anything. I've given several talks in the last few years, but very few that I actually knew anything about when I volunteered to do the talk. But part of the fun is learning. That's how you learn things, is by having to dig into something and figure it out. So the prerequisites are being interested in something and being prepared to give a talk. It probably feels a little scary, but it's not as bad as you think. But you can sort of develop the expertise and sort of take the rest of the group along on your journey as you're learning something. So I encourage people to give that a thought. It's maybe sounds a bit radical, but it's not. And so I don't think we've got too many visitors, but just in case, I'll just mention that there are lots of benefits to actually be, the meetings are open to everybody, but there are lots of benefits to being a member. There's a supportive community. We have the chat group, RASC Talk on groups.io, which is a lot of fun. People sort of share their images, but they also chat a lot about what they're doing and what's happening. A lot of mentoring and stuff goes on there. Contact Randy or just go to info at St. There it is there, stjohnsrsc.ca. To ask to join, you have to be a member to get on there. There are the publications: Sky News, which is a great magazine, the Journal, and the Observer's Handbook, which is a great publication. There are low-cost equipment rentals. There's lots of telescopes, a solar telescope, accessories. There are occasional observing sessions for members only at Butterpot, and there's a way to join there. And if you are a member, you should be getting a weekly newsletter and a monthly bulletin. So you should let Randy know if there's a problem with that. So with no further ado, it's a great pleasure to introduce Dr. Terrence Tricco. He's an assistant professor in computer science, but he was a physics student here first, so we still have a bit of a claim on him. And since then, he got his PhD in Australia at Monash University. He's a postdoc at the University of Exeter, and then at the Canadian Institute for Theoretical Astrophysics at the University of Toronto. It doesn't seem like you've been gone long enough for all that to have happened, but I guess time flies. And so he's going to talk about the modern era of computational astrophysics. So I'm going to get rid of my screen.
Let's step back. Let's step back 400 years ago to Galileo. Right. So 400 years ago, Galileo looked upwards at the night sky using a telescope for the first time. And these are some telescopes that Galileo actually used. And it was really revolutionary. Like it really revolutionized astronomy and our view. Sorry, is there all good? Okay.
If you don't, camera will pick up sound there.
Okay, don't walk off to the side. Gotcha. So looking through a telescope, right, it revolutionized their view of astronomy back then, right? Because I had this view that like the night sky and the celestial bodies, it's this like heavenly place, then everything's sort of pristine and sort of perfect up there. And very quickly realized that, you know, not everything is perfect, right? The Earth is not at the center of the universe. Galileo looked at Jupiter, the Galilean moons, right? Saw that the moon, well, these objects around Jupiter go around Jupiter. They don't go around the Earth, right? And that was kind of revolutionary in terms of the thinking at the time. And he used his telescopes to look at the moon, right? And there was a common belief that the moon was this perfectly smooth sphere because it's in the night sky, so it has to be a perfect object. And very quickly realized that there's lots of structure on the surface of the moon, right? There's craters and there's mountains and there's valleys and like, it's not perfectly smooth. So telescopes were this big change in our view of astronomy, right? And it's really propelled sort of what modern astronomy is nowadays. So this is sort of like the backdrop to the modern era of computational astronomy. If you step back to the not too far past, you'll see these sort of objects, right? We have our VHS tapes, these like old floppy disks. Computers used to look like these clunky things. We have like a 5 1/4 inch actually floppy disk sticking out of it with some very low resolution monitor. Right, and this wasn't that long ago that computers were like this. Nowadays, computers are fast and shiny, like laptops and iPads and smartphones. Like probably all of you have at least one of these devices. Right, so computers have undergone a transformation, undergone their own revolution over the past few decades. Like this phone is equivalent, like has a storage capacity of about tens of thousands of those floppy disks. And that's only in the matter of a few decades, right? There's just been exponential growth in terms of the processing power and the storage capacity of these sort of devices. And so like computers are just embedded in our everyday lives. Not, I mean, these are obviously, like, this is obviously a computer. This is a computer. Your phone is a computer. You can think of like gaming consoles are computers. You can think of, there's computers in your car. There's computers in your light switches. If there's a smart switch, there's computers in your thermostat. There's computers in so many different aspects of your life. They're just embedded everywhere. And so, you know, we live in this information. We live in this digital age. Everything is connected. We live in this digital world. Every aspect of our life is digitized and connected to the internet and the World Wide Web. We're connected in this large scale digital environment. So our personal lives have undergone this transformation, undergone this revolution based upon how powerful computers have become in the past few decades. And astronomy has undergone the same revolution with computers, right? So much of astronomy is still done with telescopes. Like here's I think a very nice image of ALMA, which is the Atacama Large Millimeter Array, which is high in the Chilean deserts, right? So it's a very dry place, very great place to do astronomy. Like we have all these telescopes here, and all of these dishes act together to act as like one large telescope. But this is only possible because of our modern computers, right? These dishes collect data. That data is stored digitally. That data is analyzed digitally. right? We need computers enabled to enable this telescope to work properly. And it's revolutionizing the kind of observations that people are making, right? One of the key early results out of ALMA was this beautiful image of HL Tau, or this HL Tau protoplanetary disk, where you have a young star here in the center, and you have this disk of gas and dust surrounding it. And there's young planets that are forming that are carving out these dark gas. Right, so there's planets here that are forming that are eating the material and trying to grow into becoming actual planets. And this is one of the first views that we've had of a protoplanetary disk at this stage, to be able to see planets forming around a very young star. And ALMA has made several more images of several other systems like this, and it's been really valuable for like confirming our understanding of how planets form and our theories of how planets form, right? So there's a whole lot of revolution that's coming through this. There's the Event Horizon Telescope, which I think is a fantastic example of how computers are making modern astronomy possible. Right here we have an array of telescopes, not just spread in the desert in one location. We have an array of telescopes spread throughout the whole Earth. Right? ALMA is one part of it. The South Pole Telescope, we have telescopes on just about every continent. Right, and so they all work in concert. They only, well, maybe I'll show the next images first, right? So what these telescopes let us do was image the supermassive black holes at the center of M87 and at the center of our own galaxy, right? Sagittarius A star. The supermassive black hole, the center of the Milky Way. And like, there it is, right? Like, there's this black hole there. There's a black hole there that actually lives up to its name. And you see the material that's surrounding it, so like a accretion disk around it. Here, like this side of the disk is a bit closer, so it looks a bit brighter, and that side looks a little bit darker, and it lines up perfectly with the theory of general relativity. But my point here is that this is only possible because we have these powerful supercomputers. We have powerful computers nowadays that can collect the data from these telescopes, actually store them, and analyze the data. So that first image of M87 by the Event Horizon Telescope, that was collected over, I think, a 3 or 5 day time span in 2017. It took them 2 years to finally release the image from the data they collected. Because these telescopes are spread throughout the world, they're all collecting their own data, and the amount of data they collected is 3.5 petabytes, which is like, this laptop probably has 500 gigabytes, maybe 256, maybe a terabyte. So the amount of data here is equivalent to possibly 10,000 laptops worth of data. Over a half ton of hard drives, like a half ton of weight of hard drives, was used to store the data from this single observation over a 4 or 5 day period. And that's a really, really challenging thing to deal with, right? They had this data distributed throughout the world. They needed to put it all in one location so they could analyze it. They can't send that amount of data over the internet. It's going to take too long. So what they had to do was take all of those hard drives, and here's an image of all of those hard drives, put them on planes and fly them to one location to put the data in one place. And we see like there's shelves and shelves and rows of hard drives. So there's a whole computational effort of how do you deal with this, right? Dealing with this is a very challenging technical computational problem aside from the observation and using the telescopes themselves. How do you do all this together? They had to fly this to a place in Germany that has a very powerful supercomputer, one of the most powerful supercomputers in the world, in order to put all that data together, to do the analysis, and produce that one single image, right? They went through this exercise again with the image from Sagittarius A star. And so that's like the square kilometer array, which is in the pipeline to come out sometime in the next decade or so. They are going to have this amount of data times 10 per day. And it's going to run 365 days of the year. Right? So like, it's an incredibly challenging problem. So computers, right, they're really revolutionizing observational astronomy. You can't have observational astronomy without supercomputers powering those systems. And I want to make the argument that computers have not only revolutionized observational astronomy, like we're still using telescopes, but the nature and how we're using those telescopes have changed. Computers have also revolutionized theoretical astronomy. And this is the domain that I work in. I'm a theorist. I don't usually work with real data or I've never actually worked with a professional telescope. I work on the theory side of things. And computers have had such a dramatic impact, both on the observational side and on the theoretical side. Here is an image of two spiral galaxies. Right, the spiral galaxies are galaxies that are undergoing star formation. They're blue in color because they have a lot of young stars that are typically blue in color. They have this like wonderful spiral structure, and you see these dark patches here, which correspond to like regions of dust or molecular clouds where new stars are forming. These are beautiful images. One of these was captured with the Hubble Space Telescope. The other is from a computer simulation. So one of these is not a real galaxy. Does anyone want to guess which one is the fake galaxy? The one on the right. So the one on the right, you can kind of tell because it looks a little bit fuzzy on the side, and like this one looks so crisp. And this is the Hubble Space Telescope image. And this one was generated using the set of fire simulations. So this particular collaboration, I'm not involved with this work directly, but they're really interested in understanding how do galaxies form? How do spiral galaxies form? Because there's a lot of questions of like, how do they generate the spiral structure? How do the various properties of spiral galaxy? Where do they come from? And so we can't run an experiment, right? We want to do science, so we want to create theories and then test those theories using experiments. But we can't make an experiment to study a galaxy, right? This takes billions of years to do. We need a lot more space than we have on Earth to build one of these. So we turn to computer simulations. We turn to numerical simulations. We take the laws of physics, we solve them on a computer. Here they start with some initial conditions. They start up with a small baby galaxy with a small seed, supermassive black hole at the beginning of it. There might be like dwarf galaxies that come in and merge to it. They might have mergers with other galaxies. There's supernovae that go off. There's a whole wide array of physics that go in that is solved, and they model the evolution of this over billions of years and see if that lines up the theories and the predictions that are made. And in particular, does it line up with the observations that we see? Right? This is the truth. Do our simulations tell us something about the truth? Do they tell us the deeper understanding, a deeper why of how something like this is created? Here's another image. One of these is HL tau, which I showed a moment ago. One is a simulation of HL tau. I just showed you the real one, so hopefully that stands out. Anybody want to guess which is the real image and which is the left one is the fake one or the real one?
The left one is the real one.
Sorry, the left one here.
Yeah,
That's the real one. You are correct. That is the real image. That's the image captured with ALMA. And this is a simulation made with the phantom code. But like, it's incredible how close this simulation is to the real image. Right? And if this simulation is, they put a protostar at the center, they have an accretion disk of gas and dust surrounding it, and they plonked a few protoplanets in there and watched them eat away at the material and carve out these gaps. Right? So it tells us, like, okay, well, now we can maybe understand this system a bit better, or potentially what are the protoplanetary sizes here, because they're too small to see directly, but maybe we can run a simulation to understand that, and then, you know, kind of confirm our theories or understanding of how protoplanetary disks work and how protoplanets might form. So theoretical physics is really reliant on these numerical simulations to test our theories of complex problems. Right? We can't run experiments. These are our experiments. These are the experiments that we have. We can do theory and try to understand, like, conceptually what is happening. Pen and paper kind of theory has driven astronomy for decades, and that's starting to run its course because the problems that we're trying to solve nowadays are so much more complex. Trying to understand how a galaxy forms or how a planetary system forms. There are so many physical processes at play. The time scale is so vast and so many interacting pieces and interacting bodies that it's very difficult to tackle that just from a pen and paper perspective. So we're reliant on these numerical simulations to test our theories. And that means that our numerical simulations, right, and the simulation codes that are used to conduct these numerical experiments, there's a few things they have to do. They have to include a wide array of physics, right? Gravity, obviously important, right? We need gravity. Hydrodynamics is fundamental. Magnetic fields is important for the majority of astrophysical problems of interest. Dust, stellar winds, active galactic nuclei, general relativistic effects, accretion disk viscosity. You know, there's the list of physics just keeps on going, and all of them are important at some level for many different problems. So it means that, you know, if you want to run a simulation, you kind of have to include everything plus the kitchen sink, because all of it's kind of important. And secondly, is that these simulations, just like the observational side of thing, where you're generating vast amounts of data, it takes a long time to analyze that data, simulations are equivalently becoming very expensive to run. And I have personally run simulations that have taken weeks of time using a large number of processors on a supercomputer that's just chugging away 24/7, trying to run one simulation. Right, so both of these are kind of problems of how do you write the code to do this, to solve all of these equations, all of these physics. How do you write this code that'll scale onto a massive supercomputer and actually run in a reasonable time frame? Because if you didn't use thousands of processors, you can imagine that it might be 1,000 times slower. And then 1,000 weeks is going to be on the order of what, 20 years? That's completely unfeasible. So I work in the computer science department. I'm cross-appointed with the physics department. My home department is the computer science department. And I'm in the computer science department because while I consider myself an astrophysicist, I'm really interested on the simulation codes and developing those codes, developing the algorithms to solve that wide array of physics, and developing the software to run on thousands of processors at a time. I want to create the tools to run these sort of numerical experiments. Right, so I work on the complete life cycle here. I work on designing the algorithms, developing the algorithms to solve all that array of physics, validating that those algorithms actually produce scientifically valid results, because at the end of the day, it's a simulation. It's not actually physics. We're using a computer to solve the equations. Depending how you do it, you might introduce errors into the solution. So you want to make sure that any errors you've introduced by solving on a computer are minuscule compared to the actual scientific accurate result you get. And maybe that only happens under certain conditions. That might not happen for all possible physical, you know, or say all possible astrophysical objects or environments that you want to simulate. Maybe it only works in certain conditions. And then I also apply these to astrophysical problems. So I do some like application of this in studying some astrophysical problems. And so I am one of the leaders of the Phantom collaboration. Phantom is used to generate that image of HL tau. We're an international collaboration of probably 30 or 40, probably a bit more than that nowadays in terms of number of users and developers. Our goal is to build the next generation of astrophysical simulation codes for everything in the Milky Way, which is a very broad statement, but it means that we are not doing cosmology, we're not studying the structure of the universe or how the universe has evolved from the Big Bang forward. We're looking at things inside of our own galaxy. So things like how do stars form, how do planets form, maybe white dwarf mergers, the environment in which stars form, the interstellar medium, the structure of our galaxy, some other things here, common envelope, maybe the binary system of two stars orbiting each other. One becomes a red giant, puffs up, and then envelops the other one. And you have this kind of a common envelope situation. All of these things are of interest to the members of our collaboration. And so what I'm interested in is developing the tools to enable all of these things to happen. One of the key lines of my research is developing and testing the algorithms to simulate magnetic fields. I'm really interested in the magnetic field side of things. It's what is called magnetohydrodynamics. So it's hydrodynamics, magnetic fields, coupled together, basically plasma. You're looking at plasma, so charged fluids. And magnetic fields are really important for a lot of different astrophysical problems. But one of the key things that sort of I focused on and that my collaborators have focused on is around star formation and the jets from very young stars. Right, so these jets, like you have a star here, you have a jet coming out of either. You have a jet coming out of the star. It's a hallmark of star formation. Gravity collapses gas down to create a star. There's a magnetic field that's involved. The magnetic field gets wound up during that process, and then eventually it pops. And it pops like this, and you get material coming out of the top and bottom, and you get these fantastic looking jets. And you can observe this, right? Like, these are some Hubble Space Telescope observations of very young star here, and you can see this jet moving slowly over time. Right? So multi-year observations, and you can see this jet moving. Some of these are incredibly fast. And so when we started, like when I first got interested in looking at magnetic fields, we didn't really have good algorithms to simulate this. So we were trying to simulate the formation of a star. So this is not a star. This is a big puffy ball of gas that's very low density. Oh, gotcha. Yep, great. So here, gravity is like taking hold. Gravity is gravitationally collapsing this big puffy ball of gas, and it's going to gravitationally collapse and form a star. And well, what happens if your algorithms aren't very good for solving your physics? I'm just going to step back here for a sec. Let me see if I can figure this out. No. Okay. I'll just pause it at points. So it's gravitationally collapsing. It's going to sort of pancake down to form a disk. Oh, okay. I thought I could pause it there. It's always different when you use somebody else's computer.
Yeah, I found that when we were trying before, I found wasn't responding to part one. Oh, you got it there.
Yeah. So this, we have this nice little disk here. It forms this disk, which is what you expect. We're looking at the disk edge on. So it's trying to form a star in the middle and have this accretion disk surrounding it. In this case, the magnetic field, we have not solved the equations of physics correctly. In this case, the magnetic field has a lot of numerical error in it, and those numerical errors overtake the actual physics that's being solved here. So what ends up happening is the magnetic field kind of goes haywire, and it basically blows your disk completely apart, and everything gets torn apart from the inside out. Definitely not how stars are formed. So we spent a lot of time thinking, how can we redesign our algorithms? How can we redesign the code that we're using to solve our equations here? Yeah, great. No, sorry. This slide first. So, right, the problem here is these algorithms are poorly designed. And in this case, they lead to the creation of magnetic monopoles. And we know from Maxwell's equations from 150 years ago that magnetic monopoles don't exist in nature. We've never seen any evidence for them over 150 years of, mathematically declaring that they don't exist. In our simulation, you can't have creation of those because we've not solved the equations of physics exactly, which means you have magnetic monopoles that can start growing. And this is not only inaccurate from a physical sense, but it leads to this catastrophic feedback effect in our simulation and causes everything to just completely explode. So better designed algorithms that target this and curb this monopole growth, if you use those algorithms to run this simulation again, what we see is that our nice disk is here, stays stable, and we see this nice jet of material come out of the top and bottom. So here's sort of like a, hopefully this is coming through on the projector well. Right, we have our disk, we're sort of looking at a bit of an oblique angle, so we're looking at our disk a little bit above it. And we have our disk here, and we see this nice jet coming out over the top and bottom here. And all we've done is fix the algorithm, fix the simulation, to solve physics more accurately. We haven't prescribed that it's going to create a jet, haven't tried to do that explicitly. We're just solving the equations of magnetohydrodynamics. We're just solving this from like a first principles perspective, and then you get the behavior coming out of it. So that tells us a lot about our theories, right? That tells us a lot about our theories because we're doing this from like a first principle physics perspective. And part of the reason why I like my work is that when you design these algorithms, they're not just applicable to the problem that you are trying to solve, they're applicable to many, many different problems. So the algorithms that we developed have been used for protostar formation, the one we just looked at. They've looked at the magnetic field or Milky Way galaxy, molecular clouds and star cluster formation. They've looked at tidal disruption events. So you have like a compact object and another star that goes close to it and gets shredded by the gravitational potential. Magnetic field, those sort of situations, magnetic field and turbulence. And people have also taken these algorithms to look at plasma fusion in a tokamak reactor. Because you're solving plasma, right? You're solving equations for plasma, charged fluid. So you have, it's the same equations fundamentally. So you have, you know, some, I guess in this case, it's meant to be like a ring, but they have like a displayed as a pipe. Then you get this kind of like kinky wiggly structure or whatever. The same set of algorithms can be applied to a bunch of different problems. So here at MUN, like my future research plans involve developing algorithms for magnetized dust. That's one of the key research aims that I have. Members of our collaboration, they've developed algorithms, two different algorithms for simulating gas and dust together. One algorithm is really good at simulating large dust grains, and one algorithm is really good at simulating small dust grains. And dust is really important for protoplanetary disks, for example, but they're really important for a lot of other contexts. One is in star-forming molecular clouds. Molecular clouds are made of molecular gas, and it's the site where new stars are formed. Molecular gas is these clouds are mostly made of molecular hydrogen and helium, and both of those you can't observe, or they very, very weakly emit. So it's practically impossible to view them in practice. So that accounts for 99% of the mass of the cloud. You can't see it, it's basically invisible. So instead, you have to use other things. You can look at carbon monoxide, or you could look at the dust in the cloud. And the structure that you see with CO is very similar to the structure that you see with dust extinction maps. So that tells you that both are pretty good tracers of the structure of your cloud, and you could sort of measure the CO or measure the dust, and then upscale that to get an estimate of the mass of the cloud or where the mass is and what the structure of that mass is. This requires understanding the dust properties to have these very accurate mass measurements. And in terms of the numerical simulations, there's a bit of tension at the moment. And this tension is that if you run simulations using one algorithm, you get a set of results where, so in this case, they're looking at turbulence. So we're trying to recreate the structure of a molecular cloud. You see these like dense filaments here. So the gas is the colored part, and the dust is all these dark points. You see that more or less like the dust correlates where the gas is. But you get all this like other substructure here. You get all this other substructure of the dust filaments where there are no gas filaments. And they observe things like dramatic factor of 1,000 increases in the dust to gas ratio. And if the dust is, which I mean, basically this means that in their simulations, they observe regions where their dust is 10 times more massive than the gas, which is to say that that region is predominantly dust with very little gas in it, which is kind of a strange thing. We've done simulations, so we have two different algorithms for doing gas and dust. We've done simulations with the other algorithm, where you expect the gas and dust to be very coupled tightly, because that's what we observe. Right? We observe the gas and dust in those CO maps, the dust extinction maps, very strong correlation. You use a different algorithm, you get that sort of behavior. Here's our gas structure, and then here's our dust structure, right? Almost a one-to-one correspondence. And so like this is one group's work using the particular algorithm. Other groups have used the same algorithm to do the same kind of simulations that see the same behavior. So the algorithm choice here seems to matter in this case. It isn't quite resolved. And it's one of the things that I want to try to understand better is the difference between these different simulations. Is this just a difference due to the algorithm? Or is there some actual underlying physics that's going on here? Are these algorithms being applied in a region where they're yielding incorrect solutions? Right, because some are good for large grains and some are good for small grains. So there's trying to disentangle what is the real physics and what is just due to numerical effects or numerical errors. That's something that I really enjoy doing. In terms of the magnetized dust, right, we have fantastic algorithms for simulating magnetic fields and hydrodynamics coupled together. And we have really great algorithms for doing dust and hydrodynamics together. But we don't have the trifecta. We don't have magnetic fields coupled to the dust. They just move independently in our simulations. So that's one of the things I really want to develop next, is to create algorithms to combine all of this stuff together to make a truly like holistic simulation. And this is really important for representing the dust dynamics in protoplanetary disks, because you have a lot of magnetic field effects that can create turbulence or incite turbulence in the disk and mix things around. And that can be really important for planet formation and really important things about the dust is distributed. And on top of all of this, so there's like, I want to create the algorithms, we want to create the code to do this. The big challenge in computational astrophysics is it really stems from trying to bridge the large scale and small scale spatial scales, right? You have things that are operating at a large scale, like a galaxy, and you have processes, say, within that galaxy that are very small scale, like a supernova going off. Supernova is compared to the galaxy, it's like a point. But you have supernova go off, they create mixing the galaxy. They drive gas together that becomes dense, that then can see the next generation of star formation. Right? So you have these very small scale phenomenon that can have impacts on the large scale. And trying to bridge that large and small scale is really, really challenging. And it's one of the big challenges in computational astrophysics right now, is to try to continue going towards that. And this is true in like cosmological simulations of the evolution of the universe. Right? They're looking at I forget the exact order, probably millions or billions of galaxies, but the internal dynamics of an individual galaxy matters for that, and it feeds back on the large scale structure. Right, so there's trying to do this as a universal problem in astrophysics and in cosmology. And it kind of correlates back to our telescopes. Right, we continue to have more powerful telescopes, and telescopes continue to grow more powerful so they can see finer detail. They can see finer detailed structure, because what's happening at the small scale is really important to try to understand what's happening at the large scale. So telescopes are doing this, and simulations need to do it for the same reason. Right? I've got a few examples here of some of these processes. Right? Supernova or jets, we're blowing material in interstellar medium. Dust coagulation, right? Happens at a very small scale. Planets are much larger than dust, but they're tied together. Turbulence. Right, there's a wide array of problems here. And here in Canada, we're actually poised pretty well to try to create these large-scale simulations. So our national computing infrastructure is run by Compute Canada. They've actually changed the name in the past year, but we can just call it Compute Canada for now. We now have several national supercomputers that have combined over 300,000 processing cores. So the power is there, right? We have it here in Canada even. So harnessing these resources will help us drive the next generation of astrophysical simulations. So I'll finish here. And I just want to say, the computational revolution, it's transformed astronomy. It's transformed astronomy in every aspect. On the observational side, in terms of telescopes, and on the theoretical side, in terms of our simulations. And it's going to continue to do so. Right? Computers continue to get exponentially more powerful. So they will continue to drive this revolution. And I think we're going to see an incredible number of transformations over the next decade, next 2 decades. And then my research is focused on like the numerical simulation side, development of the tools, the simulation tools, validating that those tools are actually doing real science, and then trying to build the software for our next generation supercomputers. That's it for me. Thank you, everybody. Yeah, absolutely.
Your simulations, that will take in to explain the why the rock items form closer and they get form further out, and your planets with the dust angular diagram. Bring that all together.
So the simulations there are simulating the dust and the gas and the star and the planets that are inside of them. We're not really looking at whether those planets are rocky planets or gaseous planets. We're not really concerned about the like internal details of the planet, because then that's just getting too small spatial scale. It'd be nice to connect that all together, yeah, but we're not quite there yet to do that specific. And like comets or asteroids, like that's also just too small scale for the simulations that we're at yet.
That's, oh, go ahead.
I was just wondering if exactly the scale, small and large scale in galactic versus universal proportions. You're saying that looking at just say a system like this, determining rock or gas, whatever, is to compare those simulations that you're saying, or to
Yeah, in some sense, you can, and kind of how this ends up working in practice is we can't simulate everything. So it'd be nice to say, okay, we have a gas cloud that's going to form a cluster of stars, and all of those stars have protoplanetary disks around them, and then all of those have planets in there that we're going to send the planets to form for a whole population. Mm-hmm. That's kind of the dream of where we want to get in general. But yeah, and so we look at like a single star or a single planetary system forming. And then you can go a little bit deeper and you could do like carve out a chunk of the accretion disk and say, okay, here's my planet, and I'll just simulate the local environment around that and sort of neglect everything else. So that's kind of the state right now. Like you do a bit of piecemeal. I'll do the small scale stuff, and then I'll create a simulation that's a bit coarser but a bit larger, and a simulation that's even more coarser and a bit larger than that, to try to, and then hopefully get some theoretical understanding of how they all piece together. But it'd be nice to have the one simulation that just does everything. Yeah.
I know that it would be easy to know if we'll see some of these types of simulations we're working on, you know, to a scale that we can apply on Earth. And we're looking at external variable plasma and rings, but cooling and space applications.
Yep. And the biggest challenge there is trying to, yeah, I guess kind of similar to you. Like you can do, if you have like a plane, for example, you do a model of that, like a small scale, and it kind of gives you the same ideas. The challenge there is sometimes maybe you can bring it down to the small scale, but trying to get the correct physical properties can be a challenge, right? You have a particular, like obviously a star is really hot, right? Like, you're not going to be able to get those sort of temperatures in a certain environment that you want. But there's things like the ratio of like magnetic energy to the hydrodynamic pressure, those sort of things, or like the viscosity, right? Fluids are viscous. In space, they're really, really inviscid, right? The viscosity is extremely, extremely low. And that level of viscosity is very, very hard to recreate on Earth in general. So it makes it difficult to try to get those, to recreate just the physical environment of like the interstellar medium, for example, just in a laboratory, even just that from the physical property perspective. Yeah.
Thank you.
Okay.
In my world, you know, simulations.
tens of thousands of atoms, like, how many particles do you have?
Right, so it varies a little bit. Kind of the scale that we're at now is around tens of millions, which is kind of small scale, to be honest. It's, we'd like to get to billions. That's our goal. And it's going to take a bit of effort to figure out how to make, you know, we have a code that can run on right now, say a few hundred processing cores. That's kind of where our code is at. We want to take it up to 10,000, because then you can go to billions of particles. But there's a huge like technical challenge of how to actually do that efficiently and make efficient use of those resources. And it's, yeah, we're trying to
How
go big.
scale with the number of particles? Number of particles.
No, it's much better than that. It's basically linear with the number of particles, which is pretty good.
And my apologies for a slight tech question, but the other thing is,
Edges, I mean,
Yeah.
you don't do periodic problems.
That's what we do.
you do, okay, so you.
Yeah.
You have many steps.
In some sense, usually the boundaries are far enough away that like the gravitational effect from the periodic star is sufficiently low, or you can turn the periodic boundaries on for the hydrodynamics of the magnetic field, a very important magnetic field. So you don't want to cut a magnetic field line in half.
I
But you-
apologize to everybody about that, but the problem with all these simulations is that you can't just stop the physics at the edge of your screen.
Yeah.
So the way people do it is they sort of reproduce the system over and over again.
But then we can selectively do that.
What's that?
Sorry.
Seems simple enough to me.
Okay.
So then we can selectively turn that on for some physics and not for others, like turn that off for gravity.
Excellent.
And our technique that we use is it can handle like free boundaries as well. You don't have to have like specific boundaries too, which is important for things like stars, which have like you have a star and then basically vacuum outside of that. And it works fine in our case for the method that we use.
Okay, great.
Do we have any questions? Oh, go ahead.
What other skill sets do you need to put together in a team to be able to do this?
Sorry, what was that?
What skill sets do you need to put together in a team that's able to tackle this?
It varies, to be honest. So I work pretty much exclusively with astrophysicists. And I'm sort of the lone person, so the outside person who's really on the computer science and astrophysics side. I'm pretty interdisciplinary in that sense. It's really important to understand there's two sides. One is the technical expertise of being able to write the code and write the algorithms and test the algorithms, understand the numerical side of things. The other is the domain expertise of you're an astrophysicist and you know what the problems are, you know what the interesting questions are, and you know, like, it can help you disentangle, okay, this is just numerical error, this is actual physical science. And then there's a lot of like data science type skills of, I have a massive pile of data that I've generated from my simulation or collected from a telescope. How do I actually analyze that data and derive some sort of scientific insight from it? So there's a few different skills there. And it kind of depends a little bit on what you're doing. In our collaboration, pretty much everybody's an astrophysicist, and they kind of pick up coding along the way. But because it depends on what you're interested in. They're really interested in the astrophysics. They have a problem they want to solve. I want to understand how planets form. I understand, like, I have two white dwarfs that are going to merge or whatever. I'm really interested in this problem, and I want to solve that problem. This is my tool to do that, and maybe it's kind of fun to do that, but that's not really what they're interested in. Whereas I'm really interested in that numerical side. So you can come at it from different angles.
Just make, an observation that seems like the algorithms are attempt at writing code that would simulate what nature does.
Exactly, yeah.
And I guess the level of code would then take the accuracy of the simulation.
That's right. Yep, that's entirely right. And kind of Mike was asking about how many particles we use in our simulation. Right, we want to use more because we'll get a more accurate answer. Right, so and sometimes the accurate answer that, like there might be a threshold level If you use this number, you'll get a sufficiently accurate answer. But sometimes that number might be out of reach currently, right? So there is a trade-off there that trying to reduce like the numerical error, so you get like it's kind of a signal to noise ratio. You get like a scientific, like physical signal coming out of your simulations.
So that explains why simulations and the real pictures you go have this fun look of simulation coarser, less refined.
Yeah, especially in the galaxy simulations that I showed, right? You get that coarsening effect. And then in those cases, like with the simulations, you have like perfect knowledge of everything in the system, right? You know every aspect of the data perfectly. And you don't always get that with a real observation. So in the two sample observations or sample simulations that I showed, they've taken their simulation data and then processed it as if it was viewed by ALMA or an equivalent telescope to make it look like it had been viewed by that telescope too. So there's also like an art of how you view the data in the end to make it look realistic, right?
Randy, if there's any questions on the line? Well, if not, let's thank Terry Dean for.
Very good.
Stay back there so the folks see it.
Okay.
We've got a presentation there. Yes, our official presentations are here, so we've got.
I was happy to just come and give a talk. I wasn't expecting anything.
Oh, well, we were thrilled to have you. And we've got calendar from the ISC. Maybe we'll do the science.
Sure. Yeah, I don't. I can have one.
That's our. Magazine. And
Randy was saying that if somebody else wants to get a Sky wants to give to a friend or something, we're not gonna get an opportunity to hand them themselves for next year, so feel free to pick one up.
Okay, thank you very much, Terry.
Yeah, thank you very much, too. Thanks, everybody.
Okay, so just
Somebody asked for a link that they wanted to ask a question about telescopes for Christmas. But they haven't joined yet, so if they do, I'll let you know.
okay, thanks. Okay, so over that. And, okay, I'll stop sharing that. Yeah, we're still figuring this out. We've only been doing the hybrid meetings for this is the third one, I guess. So, okay, so before we go on to the member observations, we've got a couple of gift suggestions, and the first one was from Randy. So I've got two views of this, one close up, and so I'm going to mute here again so that we don't have the echo problem, and you can unmute. So let me just, so I just unmuted, now I'm going to mute again. Okay, so Randy, you want to just say a little bit about what this was?
That's the Costco. Always price $189.
I didn't see, I can't see the price there. Is it on the next?
Anyway, that's a Costco. Take a chance and work it out with $20 after Christmas.
Okay, thank you. And so I'll turn my sound on again. So here's another gift suggestion, which some of you are familiar with. It's the Night Sky Almanac that's done by Nicole Mortellero, who's with the RASC. Oh, Randy's got one there. You can get it from the, it's got something for every month, you know, things that you can see in the sky, but also where the planets are. There's a sky chart for every month. It's quite a nice little production. You can get it from the RASC e-store, but they also have them at Chapters and Kohl's, but I don't know. And of course, Amazon's got them too. So another gift suggestion I came up with was this puzzle, which we actually found at the botanical gardens, but you can get them online. It just looks pretty cool. You know, somebody might have fun with that. I don't know if they've got any more at the botanical gardens, but they might. They seem to be getting those. And one more that, you know, I was just sort of going through things last night and came across this, the Lego Women of NASA. And so here's a quiz. So two of them are shuttle astronauts, and it's Sally Ride and Ray Jemison. So those people might be familiar with. This one is Margaret Hamilton. So there's the picture for Margaret Hamilton. So who knows who Margaret Hamilton was? Hands up. Yeah, you would. Did you ever meet her? No. Okay. So Margaret Hamilton, that the stack of little Lego bricks next to her is supposed to be the code for Apollo. So she was in charge of, or I don't know if she was in charge. She may well have been in charge of the software for the Apollo program. And there's a famous picture of her standing next to the stack of printouts, which apparently is the code. And the other person in here is Nancy Grace Roman. Who knows? Anybody heard of her? So she was NASA's first chief astronomer, and she's sometimes referred to as the mother of Hubble, because, you know, the idea for something like Hubble goes way back, and it really goes back to when she was in charge of astronomy at NASA. And the wide field something, infrared telescope something, I think is going to be renamed the Nancy Grace Roman telescope. So it's actually a retired set. You can't, these are getting harder to get, but Walmart actually still has them listed online, and there's lots on eBay. But the other thing I've tagged down here is that it might be fun to get a talk from somebody other than me about Nancy Grace Roman sometime. So if you want to learn about Nancy Grace Roman, you could do that by giving us a talk about her sometime. And Marcellus had a gift suggestion. Okay. So he's only showing us stuff, but I guess they're I guess they're fine over, yeah. Okay, and electric stuff, yeah, so all sorts of, anything that keeps you warm is a good gift for somebody who does astronomy. Okay, so we'll have an opportunity maybe next month too, but we're getting a little closer to the gift giving season by then. But you know, if people want to suggest some other things for, what's that? Pretty late, but maybe a last minute stocking stuff or something. What's that? Oh, yeah, I heard Randy. Yeah. Anyways, I thought this one was pretty cool. Okay, so I'm going to go through the member observations, and some of these are from people online, so I'll invite them to unmute at the appropriate times. And so we actually had a fairly eventful month. So Nikolai, Nikolai, you want to unmute? You are the only one that had this opportunity.
Yes, can you hear me?
Yeah, let me turn up the speaker and try again. Go ahead.
I can't hear you very well. Sorry, what did you say?
Oh, you can't hear me?
Now I can. I just couldn't back then. But yeah, I'll go ahead.
Okay, go ahead. It should be going through that speaker, but that's not for some reason. But go ahead.
Yeah. So this was a partial solar eclipse that I observed from Pleven, Bulgaria, which is my hometown. I was lucky enough to be there when it happened. I almost forgot about it because, you know, I know all the solar eclipses for the next 20 years, but I don't typically, you know, anticipate them to happen where I am. So I knew about this one, but I kind of had forgotten that I would be in Bulgaria for it. And so this eclipse was on October 25th, which is a Tuesday. And on the Monday, the 24th, I was having lunch at my grandmother, and she was like, "Oh, did you know that there's a solar eclipse tomorrow?" And I was like, "What? No, I completely did not know." So I had 24 hours to kind of scramble and get equipment to observe it with. So I started looking for like a welder's glass. My father had a welder's glass, but the DIN number was too low. It was 11, and I think you need 14 for a solar eclipse. It was just too bright. And then it was getting kind of late, and I was running out of options, and started to get desperate to find something. So I started going through my kind of old drawer with, you know, old astronomy stuff in it, in hopes that I would find some old solar glasses or solar eclipse glasses or something. And sure enough, in one of the folders there, I pulled out these solar eclipse glasses that were from the 1999 total solar eclipse that had passed through Bulgaria. I'm showing them here on my camera, but they were like new. They were perfect. So this is what I used, and I just used my Canon 6D camera, zoomed all the way in and right through those small solar filters on those glasses. That's how those pictures are taken. The picture on the right is the maximum obscuration, which was 35% where I was. The picture on the left is a sequence with each picture taken half hour apart. The duration was 2.5 hours. It happened in the early afternoon. Weather was beautiful. Pretty much completely clear skies. No wind, 26 degrees Celsius, which even for Bulgaria for that time of year is significantly above normal. So I just went to my grandmother's place. She lives on the 6th floor of an apartment building with a beautiful view of the sky. So the two of us just, you know, observed it, and I took some videos of her just putting the glasses on it and asking her to get a reaction out of her and what she's seeing. And those are some pretty precious videos that I have. So we had a lot of fun with it, and, you know, it was a great memory. You know, also very lucky to be there and to kind of be reminded about it from someone who doesn't generally care about astronomy. So yeah. That's about it. I don't think there were any like from the rest of Bulgaria, at least. I think the maximum obscuration was only about 40%, so it's not like I would have gained much if I traveled. So I just decided to stay home and just look at it. And yeah, that's about it.
Okay, thanks a lot, Nikolai. And let's see. So I don't think Bernard's on. So we've got a few pictures from Bernard Day, who's out towards Lewisport there with his own observatory, always amazing pictures. So this is the Andromeda Galaxy. And we've got one from Robert here, which he had some help from Jim Johnson with the processing, but this is the Triangulum Galaxy, which Robert got in a secret spot, Salmon Line. And there were actually a few shots of M33, the Triangulum Galaxy. So Jim Johnson also did one. There's some sort of mirror flips here. And Bernard again did one. You can see lots of H alpha in his. I did one, but I didn't bother putting it in here. And then John did an M81 and an M82 earlier in the summer and did it again with a lot more. There's 9.6 hours of integration, and there's not much to say about it. It's just a great shot. Lovely. In M82, you can see stuff going on in the center. That's really quite impressive. Nice work. And Jim Stacy. So we've got a couple shots of the Pleiades from Jim Stacy. So this is one from right after the last meeting, and seeing some nice nebulosity. And then, we're going to come back to Jim Johnson or Jim Stacy in a minute. And so then, I guess the same night, Jim Johnson did it, and I don't think Jim Johnson's on either, but Jim Stacy can get ready. So, Jim, you want to say something about this one? Is Jim there?
Yes, I'm here. Yeah, the Pleiades it was an opportunity to get a few more frames. That's on October 30th, which I combined with the previous set of exposures, and I was able to get something on the order of 120, 130 exposures, and I processed it two different ways. On the left-hand side, you see what I call the dusty and dirty version of the Pleiades, and this is a process to bring out the background dust. And it is a very, very dusty and dirty place, for the which is what gives rise to all the nebulosity that you see. The bright blue is the Rayleigh scattering of light off the dust, and the reddish dust is basically the galactic glow, the light that's basically reflecting off the dust that's in between the stars out there. So I particularly like the dusty and dirty version, and so later on I was trying to get more exposures and process using darks, but I haven't been able to figure out how to do darks yet. So the right-hand photograph is basically a version which basically hides all the problems I was having with my dark files by basically setting the black level so that you can't see the dust anymore. But you do see the nebulosity, and the nebulosity is spectacular in this particular shot. And 120 times 2, that's basically 4 hours of exposure there.
Great. Thanks a lot, Jim. And let's see. And Jim Johnson did a couple, and I'm right, Jim Johnson's not online, right, Randy? A couple of the California nebulae. He did 2 different palettes. So he's collecting through different filters, and then you can sort of assign. So he's doing monochrome pictures through different filters, and then you assign different colors to the data that's come through different filters. And the one where I've got the most right now, that's the Hubble palette, and so that's showing sulfur, hydrogen, and oxygen, and the other one I think is just hydrogen and sulfur. So it's basically assigning different colors, and it's the same data, and he sent out both pictures and asked people to say which ones they preferred, and they're both great. And John did, I guess you did the same sort of thing here.
First time trying it, not really sure what I was doing. Just thought a YouTube video, that's fine. Like third or fourth, first two I did it, was like, that was the same type of thing. That one broke the 3 channels, and then did a little stretch in black and white, and then tried to plot that with a Lunar layer. I believe it's quite so much red in 2 areas there. For that one.
Okay, and yeah, so what I did with yours was I just took the 2 pictures, split them in half, and mated them so that I didn't end up with 2 little pictures.
Oh, okay.
So that's kind of nice. And I did a dumbbell nebula. It doesn't look the same as those, but I had fun. And Jim, Jim has done a lot of pictures with a 5-inch refractor, which he's now moved on to a new home. So this is of historic interest because it was his last image with that. It's a monochrome image with that telescope before he passed it along. This was not with that telescope, but it's another monochrome image near the Flaming Star Nebula. And this one's, we're going to see a couple like this, but this one's spectacular. It's near Alnitak. So this is in the Orion, the constellation of Orion, but up from, I guess it's right near the end of the belt, right? And so there's the Horsehead Nebula and the Flame Nebula. So this is a wide field shot. And Jim Stacy did a similar kind of shot. You want to just say a word about this one, Jim?
Sure. Here's another processing of a very familiar, the same Horsehead Nebula shot. The brightest star in this field is Alnitak, which is in the upper center there. And that really is a big problem in processing, but it is the star that's energizing most of the light that you're seeing in the Flame Nebula, which is center left there. And the Horsehead Nebula itself is dark dust silhouetted against H alpha light emission in the background. And I processed this to get the most of the dust and dirty, the dusty and dirty backgrounds that are prevalent in this part of the sky. And so this is basically this is just 2 hours of data that I captured on that particular night, and basically processed. I'm still learning how to process this in PixInsight and Lightroom, but again, it takes a great deal of effort to bring out that dust that's in the darkest shadows to give it the sense of what it's actually really like out there.
And it's probably interesting for people, and people that have seen your stuff before know, but this is done, it's with a large lens on a camera, but it's not really a telescope, right? It's a lens that's pretty much a telescope, but it's you're really mounting a camera on a mount.
That's exactly right. This is a telephoto lens with basically this is an antique telephoto lens from the 1980s, which is it's a completely manual telephoto lens, but it's a prime lens. It's 500 millimeters and has absolutely excellent optics, which is unusual for that particular, a 40-year-old optic. But it's basically designed to be it's exactly the same design as a telescope. So I call it a non-telescope. I call it a telephoto lens, but this is a standard photography lens, which I mount on a German equatorial mount. And one of the advantages of the lens is that it's about one stop faster than most telescopes of the same aperture. So it takes me half the time to get the data that I need.
Great. Well, thanks a lot. And so this one was another one from Jim Johnson. So this is actually getting most of the action in the Orion Nebula. So up here, so this is a mosaic. So it's actually two pictures stitched together. And so up here is the Horsehead and the Flame Nebula that we've just seen from both of the Jims. And then down here's the M42, the Orion Nebula, and the Running Man, a whole bunch of stuff. So there's a lot of stuff going on in that picture. It's lovely. And a couple nights of data there. I just took a picture of the moon, very young moon, the end of October. And then a few of us on November 4th, Jupiter and the moon were very close together. So Gary took a shot, I took a shot, and Sue Hart took a shot. Sue, do you want to? Oh, no, Sue's away, right? No, Sue's here. Sue's on. Sue, do you want to say a little bit about this? So you can see she's done something pretty cool here. The exposure is just right, so you can see detail on the moon, and you can still see
Well, I
Jupiter.
can't see Jupiter on there, but it is there somewhere. Yeah.
On the screen.
Oh, yeah, just about.
Yeah, there it is.
Yes, it is up there. Yeah, I took a few shots at twilight and then a few when it got dark. And I had intended to do this on a tripod, but then didn't. So yeah, I played around with the ISO. I think that's what it was, with the various settings and things. But yeah, at least you can see the moon there. It's quite good. Yeah, I was happy with it, considering it was fairly effortless.
Yeah, I'm impressed. I handheld, everything's in focus and properly exposed. That's,
Yeah, I'm wondering if it's because I have my elbows on the railing of the deck, you know, that probably steadied it a bit. I think that's what I did. Yeah.
yeah, that's good. Okay, thanks a lot. And, oh, so we had another event. Was that only last week? I guess time flies, right? So we had, well, it's hard to remember because it was, anybody who actually saw it was up pretty early. So we had a lunar eclipse, started about 4:30 in the morning. So I went up to Signal Hill, and I think lots of people avoided Signal Hill because they figured it'd be full of crazies. And it wasn't when I took this picture, but it was by the time I took this picture, and it was pretty cold. And Richard, you took this one, right? And you had your kids in the car and the whole bit?
Yes, I started watching it, I got up early and started watching it, and then it was, when we started to go down over it behind the neighbor's house, from just getting up, like, all right, get the car now, we'll find a good spot to watch it. So I just based off where I was in the sky, I popped up on the Briar and made that turn going on T News, and there it was. I was like, all right, we're gonna watch it now. We sat and watched it until it disappeared, and then we went on home.
Yep, very good. Thanks for posting it. Oh, go ahead, Nikolai. Oh, a written comment?
I can say it. That lunar eclipse is in the same pair as the solar eclipse that I saw. They were 2 weeks apart exactly.
Right. Yeah. So every time there's a solar eclipse, is there one or two lunar eclipses that goes with each solar eclipse?
I think it's one.
Yeah. So yeah, lunar eclipses and solar eclipses always occur together. I think that's mostly true, isn't it? Not always? Okay. Okay, thanks, Nikolai. And so, Jim, you want to come on and, so Jim got famous for his solar or lunar eclipse picture, so I'll let Jim come on.
Okay, yeah, when I saw that Spot WX was predicting that it was going to be a clear morning, I was hoping to get a good night's sleep, but I had to get up early in the next morning and find. So the previous night, I was trying to figure out what a good sight line would be to get something interesting in the field of view. So I picked the skyline of St. John's, and I figured out that I had to shoot from the opposite side of the harbor, which is on the south side hills there, and I was basically using a handheld mounted on a tripod, a Canon 300mm telephoto lens. Basically what I was doing was I was exposing for the moon, and you can see that the left-hand shot basically was the partial eclipse, roughly around let's just say 6 a.m. roughly, and it was pretty dark. And you'll soon see a shot what I was actually seeing through my camera and what I was actually seeing through with my eyes. So, and the two were not the same. So this particular shot here is on the left-hand side is around 6 a.m. And then on the right-hand side is basically as the moon was dipping down below the skyline, which is roughly around 6:30. So the next slide is what I was actually seeing with my camera and what I was actually seeing with my eyes. So on the left-hand side, I'm showing the shot that was immediately preceding the right-hand side shot. And you can see that there's basically, it's exposed for the moon, but you can't see anything in the background. So basically I have to use HDR techniques to bring out the background and balance everything so that it looks like what I saw with my eyes. And so the right-hand shot is basically where I used the facility in Lightroom to basically bring up the background so that you could see the rooms and then also see the moon and the refracted light from the sun through the atmosphere, the reddish light that's basically reflected off the dark shadow on the moon and back towards the camera. So you can just barely see that there's some light in the shadow, and I pull back the highlights on the moon so that it didn't blow out. So that's basically what I did.
Yep, and that was the picture that ended up on Here and Now at the end of Here and Now on CBC that night. Okay, thanks a lot, Jim. And Chris had this shot. Do you want to tell us how you were dressed to do this shot, Chris, or not?
Sure. Can people hear me?
Yeah, I think so.
Yeah. Thanks for putting this right after Jim's amazing photograph. Yeah, wasn't actually expecting it to be clear at all the morning. I guess I didn't check Spot WX late enough to discover that it was actually going to be clear. I thought it was going to be raining, so I wasn't prepared at all. I got up in the morning, as people do sometimes before breakfast, and looked out the window and said, "Holy crow, there's the moon." Okay, totally unprepared. And I didn't have much time because it was already not visible from the house. It was behind trees. The only way I was going to get a picture of it was to run outside with a handheld camera and run up the road 100 meters. And I did so in a bathrobe and socks. And so the result is not that great. The camera also insisted on focusing on the sharp twigs in the foreground, so it's not that sharp. But at least I can say I saw the eclipse.
Yep, and you got a bit of a story for it. So.
And wet socks.
Well, sorry, what was the last bit, Chris?
And very wet socks.
I bet you did. Well, that's dedication. Okay, thanks a lot, Chris. And we'll finish up with. I forgot we got Sky this month. So we better move along. So, Yolanda, do you want to say anything about this?
Oh, I just want to say very quickly that this is actually was a beautiful lunar eclipse, and you can get a very nice westerly view from Pleasantville. And so if anyone is interested in observing at the Pleasantville, that's a very good site for both the mornings and the night viewing.
That's my secret spot.
Yeah, that's Jim's secret spot. But anyways, I know
exactly where that is.
Yeah. So I was on with walking the dog early in the morning. So it was a beautiful lunar eclipse. So pictures are not great quality. This is just to show that I was out and seeing the lunar eclipse.
Okay, thanks a lot.
I just want to say the pictures on the left is taken at the baseball field, also a good viewing site for the westerly sky, across from the Bolly Holly field.
Okay.
Golf course.
Okay, thanks. So the next thing we've got is the sky this month. So Robert, did you want to come down and run through that?
We've all seen this monthly publication before, so I try not to belabor too long. Your information there is seen, so you know when to expect an opportunity for some dark sky. And the rise and set times of our buddies in the solar system. And there's currently what the sun is sporting in the way of spots. I don't know if you can see. Yeah, nice, nice grouping there on the right-hand side. So yeah, get out and have a look if you get the opportunity. I guess they'll be gone in another day or two, perhaps. Was it 25 days to rotate? Yeah. Good. Yeah. Yeah. Then just make sure you got a filter on your, your telescope or your glasses. This would be morning planets, Mercury, Venus, and it looks like I probably should. That's funny because Mars is a morning planet. I don't know. In the morning? Right, that's my point. I missed that there. I haven't put together one of these things in how long, Nikolai? Long while.
8 years.
8 years. Forgive me if I got a few things in there a little bit off. So
you're doing great.
Yeah, thanks. So all our magnitudes, as you can see, so right now Mars and Jupiter are very prominent in our sky. So by all means, look out for that when you get the opportunity. This time of year, of course, it's getting more difficult to do that. And Saturn is receding into the twilight. I guess it's still observable. It says here 1700 hours, so 24 degrees above the horizon. Usually my cutoff is about 20 degrees for anything. So it's getting down in the muck, but you'd probably still be able to see the rings for sure. And if you want to challenge, Uranus and Neptune are a little on the dim side, but they're always that way, certainly. Oh, look at that, Uranus. It's a new name there, right? See that? I guess I can't spell. Oh, it doesn't block. Okay. And then comets, there's no big bright comets up there right now. But there are some that you can pick out in a larger scope, because you see the magnitudes here would indicate that they're pretty dim. The asteroids, by the same thing, are a little bit brighter, but they're going to look star-like, of course, and you look through a field of view of your telescope trying to identify Vesta or Pallas or Ceres. It's going to be tough. You'd have to look at the star pattern around it and then go to a publication somewhere to, you know, identify that. Or if you were lucky and you had a run of clear nights, you could actually note slight changes in the position of one of the star-like objects. Supernova, none that I know of at present date that would be of any interest to our amateur telescopes. Meteor showers, what do we have coming up? The Leonids, November 17th to the 18th. And yeah, Andromeda's late evening, but very low count on the number per hour there. But the Leonids possibility. And the moon is getting it's you know, getting dimmer now for us, so there's an opportunity there for sure. Let's see, Sky and Telescope predicts possible outburst of the Leonids up to 250 to 300 meters per hour. Yeah, yeah. And I got to note that these predictions that you see here you know what? I've seen predictions for the past 20 years, and I don't know. I don't think that there's ever been a time when it really panned out. But that's the thing. You don't know, right? It's possible. You got knots of pebbles and dust, like a ribbon. And every now and again, the earth just smashes right through that ribbon, but you got knots in the ribbon, and you don't know. They don't have the data to know, like, you know, precisely where certain knots are in that ribbon. So it's certainly possible to come across a field of debris and have a nice show. So if we're lucky and it's clear, keep your eyes open for the Leonids. And later than that, we have the Geminids, December 13th to 14th. And yeah, about that, Jim. Yeah, it's 14th, is it? I think our next meeting, yeah. Okay. But notice the number, predicted number 75 here is certainly worthwhile to keep an eye out for. So after the meeting, if it happens to be clear, then keep your eyes up. Deep sky objects for October that are optimally placed for telescope and binocular are listed, and you can just look those up and take it upon yourself to see how many of them you can see or image if you're an imager. And for November, of course, the telescopic and binocular for that month as well. Don't have an observing challenge right now. If anybody wants to suggest one online on the talk list, please do so.
Try to catch Mars in retrograde. December the 8th reaches opposition. Now it starts to go backwards.
There you go. There's our
That's
challenge.
a 3-month challenge.
Yep. Okay. International Space Station passovers. You can have a look at that there, and certainly you can go to heavensabove.com and see more. Yeah, 1,800 hours, 1,700 hours. So yeah, they're all very early evening. And let's see. I stuck this in here because there's a bit of talk on the go about this Blue Walker 3 satellite. It's a great big reflective apparatus. I don't know. What's that? Yeah, tennis court in the sky, yeah, of reflective mylar or whatever the material is, I'm not sure. But it would be quite bright if it happened to be placed correctly for us. So again, on Heavens Above, that's where you would find out, you know, when or if there are possibilities for us. No, I guess they don't know. I don't know. You think that they could though, but they don't give it. That's all you know. No, it hasn't been, or yeah, yeah. So it could be like a wow thing, you know. Certainly. Observing sessions are. I think we got to have a chat about that. You know, with the resurgence here lately of COVID, I'm not sure how that might play into what we would do or not do. So keep an eye on the talk list, which is where the observing sessions are announced anyway. And then finally, you see the November and December calendar there, just showing the phases and the meteor showers. And that's it for me. Clear skies.
So that's about it. So next meeting, just again, a reminder, it's going to be a week earlier than normal. So December 14th, don't get fooled by that. And it's going to be me talking about the Lucy mission to the Trojan asteroids around Jupiter. So I'm going to talk about what Trojan asteroids are and how, and the thing that sort of caught my attention about this is the jigs and reels that the probe has to go through to get there. It's pretty interesting. So thanks everybody for coming. I don't, Randy, is there anything else I should be announcing? There's coffee here. People at home, get yourself coffee. I'll leave the this computer connected to Zoom for another till about 9:30, and then give it back to RASC. So thanks everybody for coming, and thank you, Terry, for a great talk. We really enjoyed that. Have fun. Have a good month. Oh, and apparently there was a big rocket this morning. That's what I meant to mention. I should have mentioned that, but everybody knew that. What's that? Yeah. So people online, thanks for coming. Hope it worked reasonably well for you. We're still trying to figure out the hybrid stuff, but feel free to give us some feedback about it.